All right, I think we are ready to start, aren't we? Will, can you let people in from the waiting room?
Yeah, I will do. I'll admit everyone that comes.
All right. Will, can you do a mic check?
Hello.
All right. So, yeah, let's start this then. I'm going to start broadcast.
All right.
Is it recording?
Yeah, it says recording the top left for me.
All right. Let's do this. Welcome to week 3 introductory of Not Divulged. If you don't know who we are by now, we're a team of high schoolers and college students, largely from Texas, who are making a bunch of free classes going over competitive math. This week is Sequences in Series 1, so I'm your teacher, Naveen Mukkatt, and if you've seen the intermediate classes, you probably know me. Our TA for this session is Will, and Will, do you want to introduce yourself?
Yeah, hey guys, I'm Will. I am a senior at the Texas Academy of Mathematics and Science in Dallas. And yeah, that's pretty much it. I guess we can go ahead and get started. Naveen, are you talking? I think you might be muted.
I don't know why I got unmuted. There's no way I should be muted. All right. So we're going to start off with sequences. And a sequence is just an unordered list of numbers. So, well, sorry, it's an ordered list of numbers. There's no like real pattern to them. So 3, 5, 2, 4, 1, that's a sequence. Any other list of numbers you can think of, it's a sequence. Nothing much more to it. A series gets confused with sequence quite a bit, but a series is a pretty distinct term. We use series to say a sum of a sequence. So for example, the series of the above sequence is 3 plus 5 plus 2 plus 4 plus 1, which is 15. Now, there are a couple types of sequences in series. The first type is an arithmetic sequence, and this example is 7, 10, 13, 16, 19. A geometric sequence, which is 3, 6, 12, 24, and that should not say 4, that should say 72. That's a holdover from previous lessons. Well, sorry, I should say 40, and it's not writing. There you go. And a recurrence relation is something that uses previous terms to compute new terms. If you're confused, we're going to go all over these in depth in the next following slides. This is just to provide an example for those people who might already know what it is. Let's look over another basic definition that we need to go over. This is much more important. A term, it basically refers to a particular number in a sequence. Let's say we had a sequence that we had earlier, the 3, 5, 2, 4, 1, right over here. And let's say we call it sequence A, and we're going to use the following terminology. We're going to say that A1 is going to refer to the first term of the sequence, which is 3. And then A2 is the second term of the sequence, which is going to be 5. A3 is going to be 2. A4 is going to be 4. And A5 is going to be 1. So all these little, the subscripts below the number, like where it says A sub 1, that subscript refers to what term it corresponds to in the sequence. So A1 is the first term, A2 is the second term, etc. Now that we know that, we can finally go into what certain types of sequences are. An arithmetic sequence is one where we have a common difference between two terms. Where we have this 7, 10, 13, 16, 19 as our previous example, watch this. If we add 3 to each term, we get the next term. 7 plus 3 is 10, 10 plus 3 is 13, 13 plus 3 is 16, 16 plus 3 is 19. And we can express this in more mathy terms, like this. We're going to say that n is our first term. So n in the example would be 7. And d refers to the common difference. So d is equal to 3 in this case. So this becomes 7, 7 plus 3, 7 plus 6, 7 plus 9, and 7 plus 12 in the case of 19. And that's our arithmetic sequence. Not too hard. And as you can see, A1 corresponds to n, A2 corresponds to n plus d, A3 corresponds to n plus 2d, A4 corresponds to n plus 3d. First, second, third, fourth term. Now let's go over a problem that comes up when dealing with arithmetic sequences. If our first term is 12, our common difference is 4, what is our 8th term? Well, one way we can solve this is we can list everything out, right? We can just say 12, 16, 20, 24, 28, 32, 36, and 40. And we'll say the 8th term is 40. But this isn't exactly a satisfying answer. We just list these things out. What if they ask for like the 1000th term or something? What we're going to do is find a more mathematical way to answer this question instead of just listing everything out. Well, we know that we have to use this d in some way, right? We have to use this common difference. How can we do that? Well, we know that each term is going to be 4 more than the one before it. 16 is 4 more than 12, 20 is 4 more than 16, 24 is 4 more than 20. So let's rewrite this. Let's do this. We have 12 plus 0, 12 plus 4, 12 plus 8, 12 plus 16, ... So how can we express the 8th term in this way? Well, we know it's going to be 12 plus something, right? And we know the common difference is 4. So it's going to be 12 plus 4 times something. But what is in this parentheses? Well, it's going to be the number of terms separating A1 and A8, right? It's the number of terms separating the first term and 8th term, which is 7 terms, because 8 minus 1 is 7, right? So we'll say 8 minus 1 here. And what do you know? This turns into 12 plus 28 is equal to 40. Pretty straightforward. So please direct all questions to Will, since I can't see the chat right now. Let's go into something harder. We're going to do a general form for these arithmetic sequences. Instead of assigning concrete numbers, we want to create a formula that we can use for all arithmetic sequences. So if our x term has a value of n, our common difference is d, what is the y-th term? What is term y? Let's write out our sequence. A sub x plus d, a sub x plus 2d, dot, 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 and then we get a sub y, right? So we wanted to use the same logic that we did before. We know that a sub y is going to be in the form of a sub x plus d times something in parentheses, right? Let's get rid of that dot. So what is in that parentheses? Well, if you remember last time, the parentheses was the difference between the two terms. We did 8 minus 1. So like this time, we're going to do, instead of 8 minus 1, we're going to do y, it's not writing, I'm in eraser mode, y minus x. And that's our entire form. We have a sub y is equal to ax plus dy minus dx. And that is it. This isn't too hard to memorize. If you know the intuition behind it, you'll get it easily. Like you'll be able to come up with this in case you forget it. Let's move to a more challenged topic, arithmetic series. So in case you don't know in case you forgot what series are where you sum up a sequence. And we want to find the sum of the sequence 1 plus 2 plus 3 plus 4 plus dot 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 all the way to plus 100. If this problem looks familiar to you, you probably know the story of Carl Gauss and how he was able to calculate this in a couple seconds when he was 7 years old, when the teacher asked him. We're going to find out how he did it. Now, obviously, one of the ways you can do it is you sum everything up. You just do 1 plus 2 equals 3, 3 plus 3 equals 6, 6 plus 4 equals 10, but this is going to take forever. It's certainly not going to be doable for someone who's 7 years old. Now, how do you do it? Well, we're going to look at the midpoint of this. The midpoint is right here. What do you notice about the terms on both sides? Well, the terms on both sides they're symmetric in a sense, right? Let's say we had like a mysterious term 50.5 here. Then these two terms average to 50.5. These two terms also average to 50.5. This happens every single time. And then finally, these two terms average to 50.5. Everything averages to 50.5. That is the midpoint of this arithmetic sequence. So we can say that the answer is going to be 50.5 times how many terms there are. And, well, there's 100 terms. You're summing from 1 to 100. So the answer is 50/50. So to recap, what we did here is we took the midpoint of it, we took the average of the numbers, which also, if you guys don't know the midpoint, you can just take the average of the first and last numbers. That also works. So 50.5 times the number of terms gives you the answer. So now we want to find a general form, because why not, right? Let's find a general formula that we can use for everything. We do the same thing. We find the average of the numbers. And how did we find the average? We took the sum of the first and last terms, divided it by 2. So let's do that. The average is equal to a1 plus ax over 2. Now, here's the harder part. We have to multiply it by how many terms there are. Well, how many terms are there? Let's find out. We say that our common difference is d again. So if we had the sequence A1, A2, A3, dot, 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 A sub x, how many terms are in that sequence? Well, we can rewrite this sequence as A1, A1, A1 plus D, A1 plus 2D, A1 plus 3D, dot, 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 A sub x. How many terms are in this sequence? That's what we want to find. We know that A sub x can be rewritten as A sub 1 plus, what do you want to call this? Let's call this like M or something. Let's call it MX. Sorry, MD. So the number of terms there are is going to be M plus 1, and here's why. If there's a gap of D in between each of these, you're going to have M of these gaps, right? Here's one gap from A1 to A1 plus D, that's 1. A1 to A1 plus 2D, there's 2. A1 to A1 plus 3D, there's 3. 1, 2, 3. How many terms are there? There's one more term than the number of D's. Let's look at this block. And that circled there for some reason. There's 2 terms, there's 1 D separating them. There's 3 terms, there's 2 D's separating them. 4 terms, 3 D's separating them. If you have M D's, you have M plus 1 terms. So therefore, there are M plus 1 terms in the sequence. So how would you define that? How many terms there are? Let's solve for M. We can isolate M from the sequence, and we get that M is equal to AX minus A1 over D. That just comes from solving for M from this. So let's multiply these together. Is everyone with me here? Okay, I don't see, okay, there you go. So all you have to do now is find out there are M plus 1 terms. So let's add 1 to these. Then you just take this. This is getting in my way. And times your average. And that's your sum. I see a couple people raising their hands here, actually. If you guys have a question directed to Will, please. And Will, if I make a mistake, please let me know.
Got you.
All right, thanks. That should be 1 plus M because I added 1 to both sides. So to recap, find the average, find the number of terms, multiply them together. Let's move to geometric sequences. Now we have, instead of a common difference with the geometric sequence, we are going to have what we call a common ratio. And instead of D, we are going to use R. And let's look at an example of a common geometric sequence. We have this over here. It's 3, 6, 12, 24, 48. So what's our common ratio? Right. Well, if we multiply this by 2, we get 6. 6 times 2 is equal to 12. 12 times 2, 24. 24 times 2, 48. So how would we express this in terms of variables? We're going to call our first term a in this case. We're doing this for a couple of reasons. Just for a convention. Well, a, to get to the next term, we have to multiply by r. So we're going to get AR. We multiply AR by R again, we get AR squared. Multiply AR squared by R, we get AR cubed. That's the general term. That's the general formula for a geometric sequence. There's not really many constraints on what R can be. Like, the only one that we really have to think about is if R equals 0, because then the sequence is kind of meaningless because all of your terms just turn to 0, right? Like, it could be positive, it could be an integer, it could even be negative. It could be a fraction too. So there's not many restrictions on what R can be. Let's solve a problem. If our first term of a geometric sequence is 3 and our common ratio is 2, what is the fifth term? Well, we kind of listed it out earlier. 3, 6, 12, 24, 48 is our fifth term. But like before, we want to find a mathematical way to represent this. So let's do that. We already kind of established that here though, right? We had this AR squared, AR cubed. Let's continue that. R squared, ... How do we express the fifth term? If you remember last time, we took the difference between the terms and multiplied it by the common difference. In this case, we are going to raise the common ratio to the power of the difference between the two terms. So we're going to raise R to 5 minus 1 because that is the fifth term compared to the first term. So this is AR to the fourth. A is equal to 3. R is equal to 2. And 5 minus 1 equals 4. This is 3 times 16, which is equal to 48. Let's look at the general form because we always want to find a general form for stuff. I'm going to make a small change here. We're going to say that A sub 1 is equal to A. I'm doing this because we're going to go over series later and I want to keep the formatting consistent. Don't worry too much about them having the same name. When I refer to A sub something, that refers to a term of a sequence. When I refer to this A, we're referring to the initial term of a sequence. Hopefully you guys get that. So what is A sub x? We're going to use the same tricks we did with the previous problem. We're going to say it's in the form A R to some power, right? What's that power? Well, we said it was the difference between the two terms. So we have a 1, we have an x, so it's going to be x minus 1. And that's the general form. Let's move to geometric series. Suppose we had a series of 1, 1/2, 1/4, 1/8, 1/16. So with each successive step, we multiply our terms by 1/2, our common ratio. What is the sum of all the terms of the sequence? Because that's what a series is, right? What is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16? If you remember with the arithmetic series, we exploited the fact that there was a symmetry with the midpoint. However, this is an infinite series. We don't exactly have a midpoint to exploit. However, we do know that we are multiplying each term by 1/2 each time, right? So maybe we can use that fact to get a lot of cancellation. If you were here for our earlier introductory course over algebraic tricks, you probably remember something with nested radicals, how we assigned the entire value of this to a variable. We're going to do that. We're going to say that this equals s. And what we're going to do next is we're going to multiply our sequence by our common ratio. And now we're going to get, let's use a different color. You said red was too dark last time, right? Let's use orange. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. Our s went missing. And this is going to equal s over 2 because it's just our first sequence multiplied by 1/2. Look how many like terms we have. This matches up, this matches up, this matches up, this matches up. There's a 132 here. Everything matches up except for this one. What does that mean? It means that this entire thing is equal to s over 2. So we get s is equal to 1 plus s over 2. Remember, s is what we want to find. So if you solve this, we just get that s equals 2. Very nice. So let's find our general form. This is going to be for an infinite geometric series. So we're going to say that our first term is equal to a. Our common ratios are, what is our value of our infinite series? So what is the value of a plus a? I'm going to write the r's in a different color in a minute. So let me just write down everything first. And now I can write ar squared, ar cubed, ar fourth, dot, dot, dot. Let's use the same trick we did before. Multiply by our common ratio. Just going to copy and paste this because that's what the goal is, right? If we said this is equal to s, then this is equal to s times r, because the first sequence multiplied by our common ratio. Oops. Again, a lot of like terms. So let's subtract these. We get a is equal to s minus sr. Now we're trying to solve for s, so let's isolate it. A is equal to s, we can factor out s from the right-hand side. We get 1 minus r. So s is going to equal a over 1 minus r. Powerful, powerful trick. So our value is going to equal, a value of our series is going to equal the initial term over 1 minus the common ratio. There is a catch though. This only works if the absolute value of r is less than 1. Why is that? Well, if r is greater than 1, if the absolute value of r is greater than 1, let's go back to this, our 3, 6, 2, 12, 24, 48, our sum is going to be infinity, right? There's not going to be, it's going to be an undefined number. There's not going to be a set value. This only works if you have a sequence like that's decreasing in magnitude over time. And if R is equal to 1, the sequence stays constant and the sum is also undefined. So the most of the geometric sequences you'll be dealing with in competition math, if they're asking you to sum numbers up, it's going to be R is less than 1. The absolute value of R is less than 1. Memorize this, know how it works, but also memorize it. What if it was you wanted to find the finite form? So instead of infinite terms, you had a set number of terms. Let's look at that. General form for finite geometric series. Well, we're going to use much the same logic, so I'm just going to copy and paste a bit from this. All right, let's just say that we went all the way up to, we want to find the sum of the first x terms, right? So sum of the first x terms, the last term is going to be a to the r x minus 1, as we saw with a couple of slides ago. We're going to use the same trick. We're going to multiply the entire sequence by our common ratio. So on the right hand side we get SR. But on the left hand side we're going to get this, but we're going to have an extra term. So carry that over. And I'm going to erase the AR in front and add this. There's an extra R to the X. So we're going to subtract them again like we did before. What do we get? A lot of stuff canceled out again. This cancel, this cancel, this cancel, this cancel, this cancel. There's a couple of dots here that are missing, but you get the point. We're left with a minus a to the rx is equal to s minus, that's terrible handwriting, s minus sr. Very similar to what we did before. We're going to isolate our s and solve for it. Let's factor it out. So this is going to equal s 1 minus r. And while we're at it, we can factor out a minus a. We can factor out the a in the left-hand side too. So a 1 minus r to the x. So s is going to equal a 1 minus rx and this is going to be over 1 minus r. I believe we did something very similar to this in algebraic tricks, where we said that r to the x minus 1 is equal to r1 plus r squared plus r cubed times r minus 1. We did something very similar to that. So if you guys want to look over that handout right now, well, after the meeting, this will be recorded. So you got to recognize that you can pull tricks from other handouts, from other lessons, and apply them into current lessons. So last thing we're going to go over, the last type of sequence that we're going to go over is the recursive sequence. Recursive sequences, you guys are probably familiar with one of them. And the one you guys are probably familiar with is the Fibonacci sequence. So this is going to be 1, 1, 2, 3, 5, 18. Sorry, 8, 13. You know how it goes. So what makes a recursive sequence a recursive sequence? When we say recursion, we mean that we're using previous terms to generate current terms. What does that mean? Well, Fibonacci sequence, you sum these terms, you sum the previous two terms to create the current term. Sum the previous terms, create the current term. Sum the previous terms, create the current term, etc., etc. How do we express this in math? We say that if we call the Fibonacci sequence f, we say that f of n, so the nth term of the Fibonacci sequence, is going to equal the previous term, the n minus 1th term, plus the term before that, which is n minus 2 terms. We're using previous terms to denote current terms. That's what recursive sequences are. If you think about it, we can express arithmetic and geometric sequences under recursive sequences. How so? We can say, for the arithmetic sequences, we can say, let's use your arithmetic color. A sub n, our nth term, is equal to our previous term plus d, our common difference. We say that for geometric sequences, our nth term is equal to our previous term times r. I don't like that cross product sign. Let's use a dot instead. So arithmetic and geometric sequences both fall under recursive sequences. Let's look at our Fibonacci one in more detail. And we're going to solve a problem that doesn't look like a recursive problem at first, but we will show how. How many ways are there to tile a 1/8 rectangle? So a rectangle of length 8 with blocks that are either length 1 or length 2. There is a Fibonacci sequence hidden in this problem, and we're going to show how. Whenever you have a large number to count, it's nice to start smaller, right? Let's change our 1/8 rectangle to a 1/1 rectangle. How many ways are there to tile this with the two given blocks? Well, there's just one way. What about a block of length 2? There's two ways you can do that. You can do two 1/1 blocks or one 1/2 block. So there's two ways. What about length 3? There's three ways you can do it. You can take all 1/1 blocks, or you can one 1/1 block, one 1/2 block, and you can flip that around. So that's three ways. I'm gonna do one last one to show the Fibonacci in action. How many ways are there to tile this? You can use all 1/1 blocks. You can use two 1/1 blocks and one 1/2 block. Whoops, wrong color. And there's three ways you can rearrange this. So that's 1 plus 3. Or you can use two 1/2 blocks. And so that means you have 5 ways. So you're starting to see the geometric sequence coming out now. Oh, sorry, not geometric, Fibonacci. 1, 2, 3, 5. 8, 13, 21, 34. But why? Why does that exist? Let's think about it. Suppose we had a block of length n. How many ways are there to generate this? Instead of thinking in numbers, we're going to think in terms of other blocks, just like a recursive sequence. So I'm going to take an example of 1 by 5, just for clarity. Well, there's two ways you can create a 1 by 5 block. You can take a block of length 3 and add a 1 by 2 block in front of it. Or you can take a block of length 4 and add a 1 by 1 block in front of it. And those are the only ways you can create a block of length 5. Every single way you can create a length 5 block is embedded in these two cases. So how many ways is that? Let's say the number of ways to create a block of length n is a sub n. So this is going to be a sub 5. This will be a sub 3. This will be a sub 4. Let's use a different color. We're already using blue. Let's make this I don't know, what's a nice color? All right, that looks nice. What does this say? This says that a sub 5 is equal to a sub 3 plus a sub 4. What if you had a block of length n? Same logic applies. We say that this is block of length n. This will be n minus 2, and this will be n minus 1. So a sub n is equal to a sub n minus 2 plus a sub n minus 1. This is exactly what our Fibonacci sequence is. So now we can solve whatever we need, right? Let's look at what our problem was earlier. Our problem was to find a sub 8, a block of length 8, right? Now that we know how the recursion goes, we can continue the sequence. 1, 2, 3, 5, 8, 13, 21, 34. 34 is your 8th term. So there are 34 ways to tile a 1 by 8 block with 1 by 1 and 1 by 2. So here's a recursion problem that looks a little like almost a counting problem, but it boils down to a sequence. It's very nice. There's going to be one last thing that we cover before we go into some homework problems. I'll do 2 homework problems with y'all. What I want to go over is the recursion trick. So suppose we had a sequence where we said a sub n is equal to 3a sub n minus 1 minus 2a sub n minus 2. And we said our first terms were 1 and 1. Why are we doing the first terms 1 and 1 thing? Well, this only works if n is greater than or equal to 2, right? What if n equals 1? What if n equals 0? Which is why you have 2 parts to a recursive problem. One is the base case, and the other is the recurrence relation. The base case handles things the recurrence relation cannot. With our Fibonacci problem, this is like saying that f of 0 and f of 1 equal 1. And then we can generate the rest of the terms from there. So f of 0 and f of 1 are a base case. In this case, we'll say that our base case is a equals 0, and a sub 1, sorry, is equal to 1, and a sub 2 is also equal to 1. We want to find, let's see, a little bit of lag coming out from our app. What is a sub 8? Well, you can generate it. You can like go through each of these steps manually and find the next term. It is, though, a little time consuming. So I want to show you a closed form expression. Now, what a closed form expression is, it's a way to model recurrence, to model recursive sequences without actually using recursion. So for example, we can show like a polynomial or something. We can demonstrate a polynomial that generates a recursive sequence. And we're going to find out a way to find closed form. What we're going to do is we're going to say that this is equal to, the lowest term is equal to x, is equal to, so that this is going to equal x squared. This is going to equal x, this is going to equal 1. It seems very arbitrary, but it's just a little trick that we can use to find closed form. Now the reason why this is x squared, this is x, and this is 1 is because this is n minus 1, this is n minus 2. Another way you can write that would be a sub n plus 2 is equal to 3 a n plus 1 minus 2 a n. This bottom recurrence relation is the exact same thing as the one above, which is why you have x squared, because there's a 2 here, x is a 1, and just 1, because there's nothing here. So what does this mean? We're going to say that x squared is equal to 3x minus 2 what we're going to do is we're going to take the roots of this polynomial. And this is going to be 1 and 2, right? I'm a little sick. Our roots are 1 and 2. What do we do with these roots? We're going to use a little bit of a trick here. If you notice our Fibonacci expression, this is growing roughly exponentially, right? In fact, this is goes, if we continue the sequence, we get, it's not writing. My pencil has stopped writing. That's great. I'm going to exit out of the app and see. But we're going to get 13, 21, 34, 55, 89, etc. Yeah, it works. And in each step, we multiply by 1.6. So it's almost a geometric sequence. We're going to take some inspiration from this and see if we can express our closed form in a geometric sequence manner. And the way it turns out is if we had a sub n, it's going to equal some constant times one of our roots to the nth power plus another constant times the other root to the nth power. It's a little bit hand wavy, but it works. So what are our two roots? Our two roots are 1 and 2, right? So we say that a sub n is equal to c1 times 1 to the n plus c2 times 2 to the n. Now, how do you find c1 and c2? Well, we know our base case, right? our base case is A1 equals 1, A2 equals 1. We can plug that in and create a system of equations. A1 is equal to 1, A2 equals 1. This also equals C1 times 1 to the 1 plus C2 times 2 to the 1. This equals C1 times 1 squared, because n equals 2 this time, plus C2 times 2 squared. Let's make this simpler. We say that 1 is equal to C1 plus 2C2. 1 equals C1 plus 3C2. Sorry, that's 4C2. If you solve this, you get C2 equals 0 and C1 equals 1. What does this mean? Our closed form is an is equal to 1 times 1 to the n plus 0 times 2 to the n, which simplifies to 1. So what this closed form says is all our terms in our sequence equals 1. Let's see if that holds true. We have a sub n minus 2, a sub n plus 2 is equal to 3an plus 1 minus 2an, right? 1, 1. Let's generate our next term. 3 times 1 minus 2 times 1 equals 1. Our closed form is correct. Let's make sure it works for stuff that's not always constant, right? Let's change our initial conditions.
Naveen,
Yeah.
Could we go over this this portion again? I think there's like a lot of people who are kind of confused.
Can you say that again?
Can we go over this section again? I think there's a lot of people who are kind of confused.
Okay, yeah. I'm going to do a different case this time. Instead of 1 and 1, I'm going to say this is 1 and 3. So let's solve everything again, because some people are a little bit confused with this. So what our closed form is saying is that we're going to assign x, and then our degree of x is going to depend on what we have over here. So with a of n plus 2, we get x squared because we have an extra 2 here. With a of n plus 1, we say we're going to get x to the 1. And with a of n, it's this x to the 0. So what we're doing is we're saying that x squared is equal to n plus 2. X is equal to n. Oops, that's not right. An plus 2. X is equal to an plus 1, and 1, and x to the 0 is equal to an. These aren't true. I just want to point that out, right? This system of equations is not an actual system of equations. It's a trick we use to generate a polynomial. There's no other meaning to it. So don't think this literally means that this is 1, this is 1, this is x squared. It's just a trick we use to generate a polynomial. And getting that polynomial, we get x squared is equal to 3x minus 2. Just substitute everything back in. We solve the roots of this, and we get 1 and 2 as the roots. Those are the roots of this quadratic. So 1 and 2 are our roots. And with recursive sequences, they tend to have some kind of exponential like character. I don't know like how else I can describe this, but recursive sequences grow exponentially. So our closed form will be a sub n is equal to some constant times one of our roots to an exponential plus another constant times the other root raised to the power n, which is what you see here. It's very complicated. It took me a while to understand. So if you have to watch this a couple times over, I completely get it. And I recommend that you do, because this is a pretty hard thing to remember. But what we're going to say is that our two roots are 1 and 2 from our previous polynomial. And we have our constant C1 and C2. C1 times 1 to the n plus C2 times 2 to the n. And we changed our base case so we can go over this again. So we're going to say that this is equal to 3. Our first two terms are 1 and 3. So what is the rest of the sequence? That's what we are trying to find out. Whose mic is that? Will, can you find out whose mic that is that's going off right now?
I just did a quick mute all, and could you just unmute yourself real quick?
All right, I'm unmuted. There you go. Don't know who that was. But if our first term is in 1 and 3, we want to find the constants that generate the rest of the sequence. So we're going to say that we're going to plug in n equals 1 over here. And we're just going to follow this pattern that we have. So a sub 1, because n equals 1, is equal to 1, because we assigned that. But it's equal to our first constant times one of our roots to the nth power, and n equals 1 in this case, plus our second constant times 2, which is our other root, to the nth power, which is 1. Our second equation for n equals 2, we have a2 is equal to 3, which is what we assigned it as, which is equal to c1, which is our constant, times 1 squared, which is our root raised to the power n, plus c2, which is our other constant, times 2 squared, which is our other root to the power of n. When we simplify that expression, this equation, we get 1 is equal to c1. 1 to the 1 is just 1, so there's that, time plus c2 times 2 to the 1, which is 2c2. And then we get 3 is equal to c1 times 1 squared, which is 1, plus c2 times 2 squared, which is 4, so 4c2. When we solve this equation, we get something which is different. We're going to get that c1 is equal to -1, I believe, and c2 is equal to 1. We're getting different constants because we changed the base case. So instead of saying 1 and 1, we said 1 and 3. So this is a different expression for a different sequence. So we get -1 and 1. Let's look at our original form. We can plug these in over here, C1 and C2. And we know what our roots are, right? So our final expression is AN. Now instead of saying C1 times 1n plus C2 times 2n, we're going to say equals -1 is C1 times 1 to the n plus C2, which is 1 this time, times 2 to the n. So therefore, our nth term of the recurrence sequence we had earlier, remember our recurrence sequence was an plus 2 is equal to 3an plus 1 minus 2an, and our first two terms were 1 and 3. we get this is equal to 2 to the n minus 1. Let's see if that holds true. Our first terms were 1 and 3, right? We're going to use this sequence again. Our first terms were 1 and 3. Let's generate the rest of our terms. What is a sub 3? A sub 3 is equal to 3a sub 2 minus 2a sub 1, which is equal to, excuse me, okay, which is equal to 3, I'm going to write this in a different line, 3, 3 minus 2, 1. So our next term is 7. 3, 7 minus 2, 3 equals 15. 3, 15 minus 2, 7 is equal to 31. This matches our equation we got earlier. We said that a sub n is equal to 2 to the n minus 1, and that holds true for this sequence. So now that we discovered how to do closed form, can we do it for our Fibonacci sequence? Can we find an expression that allows us to calculate the nth Fibonacci number? Yes, we can, and let's do it. We said that f of n plus 2 is equal to f of n plus 1 plus f of n. Remember our substitutions. X squared is equal to a plus a sub n plus 2, x is equal to a n plus 1, and 1 is equal to a n. We're going to create that polynomial right now. X squared is equal to, if we substitute x, x plus 1. When we solve this quadratic equation, we get some nasty roots. We get our x is equal to -1 plus minus root 5 over 2. It looks quite nasty, right? However, this will allow us to find a closed form. Remember our expression? A sub n is equal to C1 times R1n plus C2 R2 to the n. And this n should be outside. What it's saying is our Fibonacci's the nth term of the Fibonacci sequence is going to equal a constant times this nasty number plus another constant times this nasty number. Give me a second, I added an extra negative for no reason. There you go, I fixed it. So those are our roots, those are our constants. Now define the constants requires quite a bit of work. So we're not going to do that today. I'm just going to tell you what the closed form is. So when you solve for the closed form, we get that C1, give me a second. I need to make sure I actually wrote this down right. I'm pretty sure we get that C1 is equal to 1 over root 5, negative 1 over root 5. And C2 is equal to 1 over root 5. This should have ends. So how do you find this? Well, you take your first couple terms. You know that a of 1 is equal to 1 and a of 2 is equal to 1. You get two equations, solve the system of equations, and you get these values. When you plug them back in, you're going to get f of n is equal to -1 over root 5, 1 minus root 5 over 2 to the n, plus 1 over root 5, 1 plus root 5 over 2 to the n. Whoops, that disappeared. So these are our roots from our polynomial. And these are our constants. It's the same thing we did with the other two sequences, but we applied it to the Fibonacci sequence. And if you plug in, like if you want to find the 8th term of the Fibonacci sequence, you can actually go and plug in 8 to n and you will get the correct answer. So this is a way to express the Fibonacci sequence without needing other terms. It's messy, yes, but it is useful in terms, especially if you're doing with computers, this is an easy way to generate Fibonacci sequence. If you find other sequences like this one, it provides a really quick way to solve for larger terms. Like if you wanted to find like a 25th term of the sequence, instead of having to calculate all 25 terms, you can find the closed form, plug in a25 is equal to 2 to the 25 minus 1, which is some nasty number. Let me think. I remember it being super nice. 3, 3, 5, 5, 4, 4, 3, 2, minus 1. Which is equal to this. Really, really quick. No need to calculate all the terms. So we're done with our lesson. I do want to go over 2 homework problems, just because they do have a current application to the real world right now. And they're both going to deal with geometric sequences. So suppose you had a pond, and you had a bunch of lily pads. It's not lily pads colors. If you do need to leave, you can leave right now, but I'd rather you stay for just this one thing. And let's say that the area of the lily pads doubles each day. You guys probably recognize this problem. And it doubles in each day. How many days will it take to cover a pond halfway if they cover the pond entirely in 60 days? A lot of people get tripped up. They say 30. Nope, the answer is 59, because let's say that you cover the pond halfway. Man, let me just cover it halfway real quick. Sorry for taking so much time. The area of the lily pads doubles each day, right? In the next day, it will cover the entire pond. So the answer is 59. Now that's pretty straightforward, right? But what if instead of covering half of the pond, how many days will it take to cover, let's say 1% of the pond? How many days will it take to cover 1% of the pond? Well, 1%, we can express that as 1 over 100, right? And let's work backwards. In the next day, you will cover 1/50th. The next day, we'll cover 1/25th. Next day, we'll cover, let's switch to percentage. We'll say 8%, then 16%, then 32%, then 64%, then 128%. This took us 7 days to go from 1% to 100%. So the total answer is 53 days. It took 53 days to reach 1%, and it took 60 days to reach 100%. It's a geometric sequence with r is equal to 2. Now, why did I say this corresponds to the real world? Well, in case you've been living under a rock, we kind of have a virus going around, the coronavirus. And if you guys remember, like back in like early March, we had a couple days where not that many people were sick, and then all of a sudden everything exploded. It's the same situation with the lily pads. It took 7 weeks to reach 1% of the pond, but then only 1 week to cover the entire pond. It's the same way that viruses and bacteria replicate. They follow the pattern of exponential growth. And that's why it's so important to understand how exponential growth works. The same thing works with money. With compound interest, your money can grow in the same way, or your debt can grow in a very similar way too. So understanding exponential growth is important. And this doesn't really seem very intuitive, right? Humans aren't really built for understanding the intuition behind exponential growth, even though it is such an important aspect of our lives. And that's why math is important to our lives. Thank you all for coming, and I will see you in the next intermediate class, which is Sequences in Series 2. If you guys want to stay for questions, then shoot them in the next 3 minutes before we end the meeting. Thank you so much, and have a good day.